All right, well, hello everyone. My name is Gabor. Thanks for having me. And I'm here to talk about graph databases. And graph databases, when I started my master's, they were the hottest topic out there. So every meetup you went to, it was about graph databases. It was extremely popular. So I'm curious, have you heard about graph databases before? Yes, most of you have. Have you actually used them? No, not really. OK, that's kind of a typical thing. So as I said, it was very hot when I did my studies, and I ended up doing my master's and my PhD and my postdoc in graph databases. 2 years ago, I moved to DuckDB Labs, so I'm not doing graph databases anymore as a day job, but I still have my love for kind of the elegance and how interesting they are, and I'm really happy to talk about them. But this is not my day-to-day activity, because during the day, I'm at DuckDB Labs. So in this talk, I have 3 major topics. The main part is graph databases in 15 minutes, sort of a zero-to-hero approach to give you the big categories and the significant systems of graph databases. Then a bunch of new research results that are interesting for graph databases, but actually are interesting in a more generic sense too. And then finally, it's benchmark time for databases. And for this talk, I will use this rather elaborate running example of a graph. So this is a graph that's set in Belgium and in the Netherlands, and it's set in this sub-part of the Belgium and the Netherlands where everything is just a few letters. So we have cities with letters of with names of 3 characters. We have people of 3-4 characters, and messages. And you have the edges that you would imagine between these nodes. So people know each other, they are located in a given city, and they author messages that are replies to each other. So graph databases are actually quite difficult to define, but there is one common theme that almost all the vendors seem to agree on. And this is that relational databases just cannot join. They say graph construction zone, no joins beyond this point, or no expensive runtime joins, or you should join those who left joins behind. So is it true that relational databases cannot join? This seems a bit counterintuitive. So what do they mean? So for this, I brought you a little example query. Let's say we have this graph that we have seen before, and we want to know where do the friends of the person Dan live. Now, if we have the graph on the left, we can represent it with tables on the right. So person knows person is just a relation with 2 attributes. You have person 1 and person 2, P1 and P2. And location is similarly easy. You have a person lives in a city. And if we want to know where do Dan's friends live, we filter for Dan, and then we do a join symbolized by the little bow tie symbol in the middle. And you can see that if you do it on the graph, the friends live in the cities of Mol and Os. But if you do it in this rather naive relational query where you say, select the city from the nose table joined on the location table, you only get one city, namely Os. What's going on here? Well, I just forgot that the nose edge is a bidirectional relationship that's symmetric. If person A knows person B, then person B also knows person A. And obviously, we can work around this. We can either put the logic into the query, we can insert redundant data in the nose edge, in the nose table, or more elegantly, we can just create a view on top of the nose table, and we can say we have an underscore undirected version, which is the union of the original table plus the edges swapped, and then it works. But it's already getting a bit kind of clumsy and not really nice to use. So what graph databases offer is a bunch of syntax sugar. You can say, where do Dan's friends live? Well, I'm just going to select person 1 with the match clause, which stands for graph pattern matching. That's Dan. The nose edge is denoted with these brackets. It has 2 hyphens on the side, so it's undirected. And the location edge goes to a city, and then we return to the city's name. I think this is a really nice syntax. And this is a nice syntax that captures the joins in a really visual, easy-to-follow way. And doing things like bidirectionality in the edges is kind of a first-class citizen here. So that's one thing where the graph databases are better, more elegant than relational databases. But obviously, just because of this syntax sugar, you wouldn't throw away your Postgres and existing relational databases. So there are other reasons. And in the next segment of my talk, I will argue that there are three major categories that you can think about along the transactional system to analytical system axis, and all of these solve different joint problems. So first is category 1, which solves the problem of repeated joins. What is the problem of repeated joins? Well, let's take another segment of this database and say that we want to query for the city of Mol, and we want to have all the people who live there and all the messages that they have created. There are a bunch of ways to achieve this. For example, we can just do a big join. We can say we do joins along all the edges. Maybe we do a bunch of left joins and filtering, and then we return this table that captures the entire graph. That's great, but there's a lot of redundancy in this table. We have spelled out the city of Mol and its postcode and population 3 times over. There are a bunch of nulls, and on the client side, it's rather difficult to reconstruct what's going on because you just get a big table and you don't really know which part belongs to where. So this is called overfetching, and it's not really a great user experience. It also ends up transferring maybe megabytes of blobs over the wire. So what we can do instead is that we can first get the town, then we can get the people who live in it, and then we can get their messages. So we keep going back and forth on the wire, and we keep fetching the data that will give the next entity and the next part of the data. This is known as underfetching, or the n+1 query problem, because we always need to do one more query just to get the data that we want. And this seems to be like a rather fundamental, difficult problem, and it is. It's known as the impedance mismatch problem from object relational mapping. It's really difficult to take a relational data set and map it to an object-oriented data set or a graph-like data set. However, this, because it's a difficult and well-known problem, has been solved by the GraphQL community to some extent. In GraphQL, you can do these queries where you specify in a hierarchical way what you want to return. And it usually returns a JSON. It just has to be a nested data set. So this is one way where we do one query, so there is no overfetching or underfetching, and there is no redundancy. It's actually really nice and elegant in the return data set. And GraphQL was actually adopted by a bunch of graph databases, for example, the dgraph system. Dgraph is a distributed system that goes for high throughput. It's written in Go, it ships its own key value store and caching layer, and it does the DQL language as the primary interface to interact with. At the bottom of these slides, I have always these kind of data flow style diagrams where I try to illustrate the project's path. And dgraph had a particularly difficult path because they went through 3 major licensings and 4 licenses in total. It also had a fork that has died off. So unfortunately, I will not always go through this, but this is really typical that systems started out with some really nice open source license, and then they forked off, and then some of them turned proprietary, other parts maybe got relicensed, and it's just not a nice landscape overall. Cosmos DB is a Microsoft solution. This was not a really well-known system, but they have this really famous use case now that they power ChatGPT. So the conversations that you do with ChatGPT, OpenAI puts them into a Cosmos DB instance. What Cosmos DB provides is that it has SQL, but it has a really special dialect of SQL, where the joins are actually turned into this dot operator. So you can say e.name.first or e.department.name, where e is the employee. This is something that again solves the join problem where you need to traverse down certain edges. It's just syntax sugar for that sort of traversal. It's very close to being something like MongoDB, and this is exemplified by the fact that Microsoft recently forked off parts of the proprietary code and made it open source available under the MIT license, and it's called DocumentDB. So it's kind of a document store. There are a bunch of other systems here that I will not go through in detail. You can see that they either ship their own query language, or they use Gremlin, SQL dialect, or GraphQL. If you are looking for a graph database system and you want a system like this, just look for multimodal system, which also works as a document store. That's usually a telltale sign that this is a graph serving system that solves this repeated join problem. And if you want to put a label on it, I think this is like the MongoDB of graph databases. Now, the second category is what I call classic graph databases, and these solve the problem of recursive joins. What is a recursive join? A recursive join where you don't know how many joins you do exactly, but you define a fixed point criterion, and then you run the join until you reach that fixed point. A really typical use case is shortest path finding. For example, how many hops are there between Dan and Finn in this social network? You can see even on the picture that is just, Ada and Carl, so that's the path. But if you want a SQL database to tell you this, you have to write a monstrosity like this. I spent quite a lot of time with this query, and this is as nice as I could get it. It has nested data to keep track of the path. It has window functions to check whether the nodes have been visited. It has 2 parts of the union, and it's really not pretty, not efficient, not nice, and not great. In Cypher, however, this is really elegant. You just say, I want the shortest path from this node to that other node along the nose edges. I think this is as simple as it gets, and if you have a lot of these sort of queries, then graph databases make perfect sense. Neo4j in particular is the first modern graph database. They introduced the Cypher query language, and they have taken a lot of work on their shoulders to turn it open source and to standardize it as GQL. And they also did a lot of great advocacy work, publishing books, running meetups, and everything. Other graph database systems are here. AWS has its own system called Neptune. There are systems like GalaxyBase, GraphScope, MemGraph, and so on. Google recently rolled out something called Spanner Graph. I think labeling-wise, this is Postgres. It's Postgres, but it also does the path queries really well. And then finally, we have something called Graph BI, which is where it kind of blends into the territory of relational systems. And it does so by solving 2 queries, interestingly. So I told you that we have this elaborate example, but it's actually not enough to illustrate everything. I needed to add more stuff, which is these pink nodes on the left, which capture certain topics. And these topics are music genres like rap music and rock music. And a typical recommendation style query would be like, let's find people who have lots of shared interests, and maybe we can just give them tickets to those sort of interests if there's a concert nearby. So if we say we want shared interest, we can run a query like this. We do the nose edge, one interest edge, another interest edge, and then we intersect them in the middle. So you can see that we have, for example, Ada and Bob having 2 shared interests, and Ada and Carl having 1 shared interest. So this doesn't seem that difficult computationally. But what makes it difficult is that if you formulate this in a relational database with the 2 join operators that I explained, it will always be quadratic. No matter how you try to shift the joins, how you try to reorder them or use any commutative or associative rule, it will not work, and it's just fundamentally not possible to do it in a classic relational system. So your Teradata will blow up, your Snowflake will blow up, your DuckDB will blow up. What we can do is something called a multi-way join, which actually reads from all tables, all 3 tables in here, and that brings it down from quadratic to m on the power of 1.5, and that makes all the difference. So this is something that graph databases can help if you have this graph BI problem. The matter of fact is that in reality this is quite rare, so it's rather rare that you have these cyclic queries and they cause a big issue to you. What's more common is that you have acyclic queries. And there is a macOS update ready, which, yes, sorry. I will probably need your hand for that. Thank you. Okay.
I think this is yours.
Perfect. So here's a query. It's rather antisocial, evil little query, which says which persons have more topics of interest than friends in the network. And you can gauge it again, and you can see that if you write this query, which does aggregation and then compares the results of the aggregations, Bob has 5 interests, but only 2 friends. So he would be the one we would target with this query. The problem here, again, is that we have these huge intermediates. We have 5 topics that we have to repeat for every single person that Bob knows. And we have 2 friends at the moment we have to repeat for every single new hobby that Bob acquires. This will also blow up and will also be something that just doesn't finish on any contemporary relational database system. And the idea of factorization is that this is a really predictable pattern of redundancy that you can compress away using a lossless compression method. And this is called flat representation to factorized representation. You can take a classic relational table and you can turn it into the union of Cartesian products. And if you see the factorized representation, it's actually, even just by looking at the table, obvious that Bob will be the result because Bob has 5 topics and 2 people, and obviously 5 is bigger than 2. And this is something that basically any workload that has many-to-many joins could benefit from. This is very common in analytics. And this is now kind of understood to be important, but this is still a part of active research. So we don't know how to factorize long chains where we have different cardinality edges. We don't know how to implement it efficiently or how to return it to the client using the existing infrastructure. But I think this could be figured out eventually, and then it could also be useful for the problem that we started with, returning compact graphs in one query where we join together different tables. In the analytical database side, you can use systems like TigerGraph. This is a system that focuses on path queries, and it has its own custom query language that does traversals really nicely. Or you can use something called DuckPGQ, which is a system that is developed at the CWI, and I have been involved with this in the early stages of the project. This uses something called SQL PGQ, which is the new graph-specific extension to the SQL standard, and you can do like Cypher-style graph queries in the SQL language. So in short, if you want to label this, this is like Teradata for graphs. It does many-to-many joins more efficiently. Speaking of more efficiently, graph databases don't have the best reputation when it comes to performance, and that's because they are rather immature systems with optimizations that are lacking. So to this end, I work in a nonprofit called the Linked Data Benchmark Council, where our mission is to accelerate the progress in the graph data management field by making systems comparable. And we achieve this by taking our membership, which is mostly 25 organizations and 100 individual researchers and scientists. We put these companies together in the same organization. We make them accept our rules. And then we take these database companies, the hardware vendors, the cloud providers, and all the vendors, and we say that you should collaborate on standards like query languages and benchmark, but you should also compete on performance. And we have these leaderboards where you're basically publicly shamed if you don't compete on performance. So what do we do with this? Well, I will just briefly touch on a single workload, which is called the interactive workload. The interactive workload you can think of as browsing around Facebook and then clicking on stuff and then getting different results in your feed. And obviously, being a graph benchmark, we selected the queries such that even though you can formulate them in SQL, sometimes even in non-recursive SQL, they're much nicer if you formulate them in a graph language like Cypher, SQL PGQ, or the GQL standard that came out last year. And I think so far it has been working. If you look at this diagram, which is the time axis on the x-axis for years, and the number of operations on a logarithmic scale, you can see that we have this really nice speed up, basically with the throughput of the systems doubling every year, and the price performance is actually improving even better. What's interesting about this picture is that all 5 vendors depicted are from China. China has a really nice venture capital ecosystem that kind of rewards this competition on performance, and the vendors really work hard to get good results. Now, an interesting notion is the little red dot. It's not the fastest system, but this is the fastest system that uses a declarative language. This is the Huawei GES, the graph engine service, that is not only really fast, but it's actually making use of many of the techniques I've just shown. So it uses factorization, and it uses a sophisticated optimizer to make sure the queries are fast. So what are the challenges in the graph database space? I think the main challenge is that the hype cycle has moved on before the systems matured. So graph database systems have been kind of getting a lot more popular over the course of 10 years. They've grown to 13x compared to the initial popularity. But they have been on a decline for the last 2 years, which is obviously not great. One thing that the vendors are really interested about is GraphRag. It's the lifebelt that every single vendor seems to jump and trying to cling on to. We'll see whether this will work in the long term. So to sum up, if you have many joins in the query and your query seems to be difficult to write and underperforming, you may need a graph database, but please think about what sort of graph database you use. Because I have seen many times that people pick something like a MongoDB style graph database and run an analytical Teradata style workload on it, which is just kind of a recipe for a performance disaster. So consider this, check the licenses, and check the performance results. Thank you.